In this chapter section, you will learn about titrations. Please read the OER textbook for more details. A titration is a technique used to determine the unknown concentration of a basic or acidic solution by reacting with known concentration of an acidic or basic solution. Titration analysis has various applications ranging from medical uses all the way to environmental science uses. For example, in order to determine the portion of the medicine, the titration can be used for that. Or if you want to determine the concentration of nitrate or ammonia in water sample, you can also use titration technique as well. In this course, for the laboratory exercise, you will learn about how to use titrations to determine the content of the acid in the juice beverage, and also how to determine the acid in different brand of vinegar. The general experimental setup for titration consists of burette, titrant, and analyte. Burette is an apparatus used to measure the volume of the liquid. Titrant is a solution that is filled in the burette with the known concentration. And analyte is a solution inside the aluminum flask with the unknown concentration, whose concentration is to be determined. The titration between acid and base rely on the neutralization reaction that we learned previously. The titration is stopped when the mole of acid equal to the mole of base. We call this point an equivalent point. In general, the equivalent point is the point where the titrant completely reacts with the analyte. At this point, mole of the titrant is going to be stoichiometric equal to the mole of the analyte. And the indicator can be used to detect the equivalent point visually. For example, phenolphthalein is a common indicator that changing from under acidic solution colorless to pink in the basic solution. For example, in the case that the analyte is an acid with the unknown concentration and the titrant in the burette is the known concentration of the base, you are going to add the indicator inside the analyte, and what happens is that as the base is keep adding into the analyte, it's going to neutralize with each other up until it's reached the equivalent point at a certain pH. The color will then change from the colorless to light pink. Whenever it's reached the light pink, or whenever that it's reached the equivalent point, you are going to stop the titration. And the volume that we use for the titrant until it's reached the equivalent point, we call this volume the end point. The volume of the titrant at the equivalent point is called the end point. This volume at the end point allows us to calculate for the molarity of the analyte. You are going to see this experimental setup again when we look at the lab, when we determine the content of acid in vinegar. The calculation example for titration is similar to the acid-base stoichiometry that we learned earlier. For example, example 1 asks to calculate the molarity of acetic acid in vinegar sample, and is giving you with this information. This example 1 is similar to the lab that we are going to take a look at later on. For this example, I will use the same analysis that I did before when we talk about acid-base stoichiometry. I'm going to start with each of these given information. 25 milliliter contain 1 unit. This is of vinegar sample, and we also given 35 milliliter. This is also contain 1 unit of sodium hydroxide, and we have 0.02 molar of sodium hydroxide. This unit contain 2 units, which is mole over liter. So that means the 0.02 can be used as the conversion factor. For the experimental setup, for example, 1 would be the vinegar would be the analyte because we don't know the concentration, and sodium hydroxide would be filled in the burette and become the titrant because we know the concentration of sodium hydroxide. And this reaction will then stop once it's reached the end point. The end point is the same as an equivalent point. At this point, you will need to know that mole of the acid in vinegar is equal to the mole of the base. The balanced chemical equation of this neutralization reaction can be written as sodium hydroxide react with acetic acid in vinegar to become sodium acetate and water. And at the equivalent point, the acetic acid in vinegar will be the same number of mole as the sodium hydroxide. And according to the balanced chemical equation, you can see that the stoichiometric ratio for the reaction between sodium hydroxide and acetic acid is 1:1 ratio. That means if 1 mole of sodium hydroxide is consumed, 1 mole of acetic acid will also be consumed as well. If 5 mole of sodium hydroxide is consumed, 5 mole of acetic acid will also be consumed as well. So that means if we know mole of sodium hydroxide, we should also know mole of acetic acid. And if we know mole of acetic acid and know the volume of acetic acid, we should be able to find out molarity of acetic acid in vinegar sample. So I'm going to go ahead and find out number of mole of sodium hydroxide first by using molarity of sodium hydroxide and volume of sodium hydroxide. Then use the mole-to-mole ratio between sodium hydroxide and acetic acid to convert to mole of acetic acid. And the molarity of acetic acid in this vinegar sample would equal to mole divided by liter. And the molarity of acetic acid in this vinegar sample will come out equal to 0.028 molar. The titration technique is not only used to determine the unknown concentration of the analyte, but we can also use the titration technique to identify the molar mass of the analyte as well. For example, if you have this many grams of an unknown monoprotic acid, and this unknown monoprotic acid is titrated with sodium hydroxide, it tells us that the initial reading volume of the titrant is 3.55 milliliter and the final reading volume is at 40.84 milliliter. It asks us to calculate for molar mass of this unknown. And here is the experimental setup for example 2. The titrant that we will use is the sodium hydroxide in the burette, and the unknown monoprotic acid will be in the Erlenmeyer flask. Note that the burette scale will start from 0 all the way to 50 milliliter. That means that the 3.55 milliliter will start closest to the 0 end, and 40 milliliter will be the one that close to the 50 milliliter on the scale of the burette. This tells us that the volume right here between 3.55 to 40.84 would be the volume at the end point where the mole of the acid is equal to the mole of the base. And again, the end point is when we stop the titration because the indicator changed the color for us to see visually that it's already reached equivalent point. The neutralization reaction between sodium hydroxide and the monoprotic acid can be written as this. Sodium hydroxide reacts with monoprotic acid, convert to salt and water. Note that the unknown acid identity is monoprotic acid, which means that within this acid there is only one available proton to donate. This gives us the information that the sodium hydroxide is going to react with the unknown acid with the 1:1 ratio, which means that if we know mole of sodium hydroxide used, we are going to know the mole of the unknown acid that is consumed as well. Therefore, the first step is we need to find mole of sodium hydroxide by converting the volume that is used for the sodium hydroxide, use molarity of sodium hydroxide and convert to its mole. Then convert this mole of sodium hydroxide into mole of the unknown monoprotic acid by using the stoichiometric ratio between the two. To calculate for molar mass unit is grams per mole. Therefore, in order to calculate molar mass of the unknown monoprotic acid, we are going to divide the given grams by the mole that we just calculate. And we will get the molar mass of the unknown monoprotic acid equal to 160 grams per mole. To practice more of this type of calculation, please complete the DIY problem on page 50, number 1 and 2. The answer for this will be given on Moodle. Next, we will take a look at the titration curves. There are two curves that we are going to consider. One is when an acid is titrated with a base, and the other is when a base is titrated with an acid. When an acid is titrated with a base, it implies that an acid is the analyte and a base is the titrant. And vice versa, when a base is titrated with an acid, a base in this case would be an analyte and an acid would be the titrant. When we plot the titration curve, the volume of the titrant will be on the x-axis. And for the first graph, this volume is going to be the volume of a base such as sodium hydroxide. The y-axis will represent the pH of the solution inside the eliminator flask, which is of the analyte. At the beginning of the titration, before any base is added to an acid, the pH of the solution will be a very low pH. It's indicated this solution is an acidic solution. And as we keep adding more of the base, as the volume of the base increase, or when we add the titrant into the flask, you are going to observe the pH increasing until it reaches the equivalent point. At the equivalent point, the pH will increase the steepest. And beyond the equivalent point, when we have excess base, the pH will continue rising. The middle between this part of the graph where the pH increase the steepest, in the middle of these, we call that the equivalent point. Again, this point is when the mole of acid equal to the mole of base. And if you trace these down to see the volume, this is the volume at the equivalent point where we call the end point. And again, if you trace this point to the y-axis, we can see that this is the pH at the end point. Now let's consider the second graph. The second graph, when a base is an analyte and an acid is the titrant, the graph that we are going to plot would be the volume of the titrant. In this case, it would be an acid, such as HCl. And the y-axis would be the pH of the analyte, which is going to be the pH of the base inside this eliminator flask. And again, at the beginning of the solution, before we adding any acid into the flask, the pH of a base should be a very high pH, higher than 7, indicated this solution is the basic solution. And as we keep adding acid into the analyte, the acid will neutralize the analyte base and causing the pH to continue to decrease because the solution becomes more basic, until it reaches the equivalent point, and the pH will change rapidly at the equivalent point. And beyond the equivalent point, we'll have excess acid, and the pH will continue to going down slowly. And again, in the middle of this, at the steepest point, this middle right here, this point is the equivalent point where the mole of acid equal to mole of base. And the volume at this point would be the volume of the end point, and the pH would be the pH of the end point. Next, we will take a look at the pH at the equivalent point. The neutralization reaction between acid and base will produce salt and water. Therefore, in this case, the salt property will tell us about the pH at equivalent point, and here's why. At the equivalent point, the mole of acid and the mole of base are equal, which means that when they react, both of them will be all consumed. At the end point, there will be no molecule of hydrochloric acid or sodium hydroxide left. It will have only sodium chloride and water present. For example, at the equivalent point, if mole of hydrochloric and sodium hydroxide are equal to be 1 to 1, at the beginning, before these two will react, there will be no sodium hydroxide. But once they react, these two will be consumed because they are 1 to 1 ratio. Every 1 mole of hydrochloric acid will require to react with 1 mole of sodium hydroxide. That means the change would be negative 1 mole. And the mole of sodium chloride that will be produced would be 1 mole. Therefore, at the end, after this reaction finish, you are going to end up with 1 mole of salt that left in the solution. Therefore, this salt sodium chloride will determine the pH of the solution. This analysis can be used for the rest of the acid-base titration, whether it's between strong acid and strong base, or weak acid and strong base, or strong acid and weak base. You will still see that at the end, at the equivalent point where all the mole of the acid and base react, at the end point, you are going to end up with the number of mole of the salt left. So that means in this case, we are going to need to know the property of the salt, because that's the only species left at the equivalent point to help us determine the pH of the solution. We learned about how to determine the pH of the salt before in the chapter 14.8. We are going to use the same concept to apply here. For the hydrolysis of salt, sodium chloride, when sodium chloride undergo hydrolysis, it will dissociate into sodium ion and chloride ions. The sodium ions under the ionization in water is going to accept the OH from water and give off a proton. However, the product of sodium hydroxide, this is a strong base, which means that it's most likely to dissociate into ion. It doesn't want to stay as the molecule. Therefore, this reaction will not occur because the strong base is most likely to dissociate in the other direction. Therefore, in this case, because sodium ion will not react with water, sodium ion is going to be pH neutral. Same analysis for chloride ion as well. Chloride ions, when it react with water, it will become hydrochloric acid and hydroxide ions. And again, hydrochloric acid is a strong acid. It's most likely to dissociate. Therefore, the forward reaction is not going to happen. And in this case, chloride ion will not react with water. Therefore, we say that chloride ion is pH neutral. That means the overall sodium chloride is going to be pH neutral. Therefore, as you see at the equivalent point, when you have the strong acid react with the strong base, the pH at the equivalent point would be 7 because it indicates that this salt is pH neutral. Now, if you look at the neutralization reaction between weak acid and strong base, the salt that produced at the equivalent point is, for example, sodium acetate. Sodium acetate undergo hydrolysis to dissociate into sodium ion and acetate ion. We just saw previously that sodium ion would not react with water, therefore sodium ion is pH neutral. However, for for the acetate ion will react with water to form acetic acid and hydroxide ions in the solution. In this case, we see that the acetic acid is a weak acid. Therefore, acetic acid would undergo reversible reaction to form acetate ion in water as well. So that means this reaction is possible and the acetate ion will react with water. Therefore, in this case, because acetate ion produce hydroxide when it reacts with water, therefore the acetate ion would be basic ion. In this case, when you have neutral pH ion combined with the basic pH ion, the overall salt would be a basic salt. Therefore, at the equivalent point, you can see that the pH would be greater than 7 because it indicates that the salt solution is a basic solution. Next, let's take a look at when the strong acids such as hydrochloric acid react with a weak base such as ammonia. The salt that will be produced would be ammonium chloride. At the equivalent point where there is no more acid and base, is only salt left, you will have salt of ammonium chloride that can hydrolyze in water into ammonium ion and chloride ion. The ammonium ion can then ionize or react with water, and because ammonium ion contain extra proton, so it's going to give off proton to water and become ammonia and hydronium ions. Note that the ammonia is a weak base. Therefore, this reaction is a reversible reaction, which means that the ammonium ion can react with water, and also the ammonia can also react with hydronium ions. Therefore, in this case, because ammonium ion produce hydronium ions, therefore the ammonium ion would be an acidic ion. And we see previously for the chloride ion will not react with water. Therefore, the chloride ion is pH neutral. When we have the acidic ion paired up with pH neutral ion, the overall salt would become an acidic salt. Therefore, at the equilibrium point that contain acidic salt will have the pH lower than 7. Next, we are going to take a look at how to calculate pH for the titration solution between strong acid titrate with strong base. In this case, you can see that the strong acid and strong base, when they react, they will produce pH neutral salt. The way that I memorize this is that when the strong react with the strong, the result would be neutral because the strong and strong, they will be able to cancel each other out, so the salt will be the pH neutral. Example 3 asks to plot a titration curve between strong acid HCl that titrate with sodium hydroxide. In this case, we need to identify first which one is the titrant and which one is the analyte. When the HCl is titrate, this implies that HCl is the analyte. And when it's titrate with the strong base, we see that the sodium hydroxide is the titrant. Therefore, in order to plot the graph, we will plot between the pH of the analyte versus the volume of the sodium hydroxide, which is the titrant in this case. And as we see previously, before the reaction starts, the pH of the analyte, which is strong acid, hydrochloric acid, would have a low pH. And as you keep adding sodium hydroxide, the reaction will become less acidic and more basic. Therefore, the pH will keep rising up until it's reached the equilibrium point. The slope of this graph will increase sharply. And then once it's past or beyond equilibrium point, when there is excess titrant or sodium hydroxide, then the slope will increase slower and keep going up because the sodium hydroxide is the base. So the pH will keep rising up. And again, the equilibrium point would be the point in the middle of this steep slope. And the volume of the equilibrium point would be the volume at the equilibrium point here. This is the volume of the endpoint. And the pH of the endpoint would be right there. And because this is the reaction between strong acid and strong base, therefore, at the equilibrium point where it's only salt left, the pH at equilibrium point would equal to 7 because the salt has pH neutral, as explained earlier. And our goal in this section is that we are going to learn how to calculate pH for each of these points of the titration curve. For example, point A, where we have not added any base yet, and there is only acid available in the flask. Then we will learn how to calculate the pH at point B, where when we already add sodium hydroxide, but the sodium hydroxide is the limiting reactant, and we have excess hydrochloric acid. And we're going to calculate pH of this point. Then we are going to look at the pH as point C when it's reached the end point. And we are going to also look at the beyond endpoint as well, which is point D. And we are going to calculate what is the pH at this point when we have excess sodium hydroxide, but all of the hydrochloric acid is all consumed. Point A, this is the point where the neutralization doesn't occur yet because we have not added any base yet. At this point, the pH would be the pH of the acid that is available. And the given point A is that the acid that is available is 0.01 molar hydrochloric acid. And we learned earlier in chapter 14 that the pH of a strong acid would equal to negative log of its concentration. This is because hydrochloric acid is strong acid, so the concentration will dissociate 100%. Therefore, the concentration of proton will be the same as the concentration of the strong acid. If you take a negative log of this value, you will get the pH equal to 2. point B is when the neutralization reaction will occur because we keep adding sodium hydroxide into it. Therefore, we will need to set up RICF table. And the unit of RICF table have to be in mole unit. To get the mole of each of these species, you are going to take the volume that is given, convert that to liter, and multiply by molarity to get mole of hydrochloric acid. And for mole of sodium hydroxide, you are going to do the same thing. Take the volume, convert that into liter, and then multiply by the concentration. You are going to get the mole of the base. So the initial mole of hydrochloric acid would be 0.0002 mole. For the sodium hydroxide would be 0.0001 mole. And for sodium chloride would be 0, and we can ignore water. You can see that at this point of the titration, the number of mole of sodium hydroxide is less than hydrochloric acid. Therefore, sodium hydroxide is the limiting reactant in this case. So the amount of sodium hydroxide would be all consumed. And it's going to be the same ratio as for hydrochloric acid. And would be the same number of mole that will be produced for sodium chloride. And at the end, after this reaction complete, when they react, you are going to have only 0.0001 mole of hydrochloric acid left, and you will have no more sodium hydroxide left, and you are going to have 0.00010 mole of sodium chloride left in the solution. Now, if you look at what left after the reaction, you will see that we have strong acid, hydrochloric acid left, and we have salt, sodium chloride left, but this salt is a pH neutral salt. Therefore, we don't need to actually worry about this salt because it won't have no effect on the pH of the solution. The only thing that will have effect on the pH of the solution would be the strong acid. Again, this is a strong acid. Therefore, in order to find out pH, we will need to find out the concentration of the proton in order to put a negative log in and then get the pH of the solution. And we already see that because this acid, HCl, is a strong acid, therefore the concentration of the strong acid would equal to the concentration of proton, which means that before we can take negative log of concentration of proton, you will first need to find the concentration of hydrochloric acid. The concentration of hydrochloric acid can be calculated from using the number of mole that present in the solution. At this point, we have only 0.00010 mole. We are going to divide this mole by the liter of the solution. In this case, if you think about it, initially we have only 20 milliliter of HCl, but then we are adding another 10 milliliter of sodium hydroxide into this solution. Therefore, the total volume at the end would be 30 milliliter. Convert 30 milliliter into liter, you are going to get 0.030 liter. Therefore, the concentration of hydrochloric acid would equal to 0.0033 mole per liter or molarity. Then take negative log of this value, you are going to obtain the pH value, and you will get the pH of 2.48. And again, this is a basic solution because we have not have enough sodium hydroxide to react with the acid yet. Therefore, the pH would be still under the acidic range. If you compare between the first point A and point B, you can see that the pH will slightly increase. The reason for that is because we have not added enough sodium hydroxide yet. But again, the pH will need to rise from point A to point B because you are making, as you add sodium hydroxide into the solution becomes less acidic and more basic. That's why the pH will need to increase to be more than point A. Now let's take a look at point C. Point C, given that the concentration and the volume of an acid is equal to the concentration and the volume of the base. Therefore, at this point, if you find out the number of mole, you can see that the mole of acid given is going to be the same as mole of base given. Therefore, at this point, we can see that both of them will react and it's going to reach the equivalent point where the two moles are equal. Therefore, at this point, there will be no longer hydrochloric acid and sodium hydroxide exist. It will be only salt, sodium chloride exist. Therefore, the pH of this solution would determined by the property of the salt, which is going to be pH neutral for sodium chloride. Next, at point D, if you compare between concentration and volume, you can see that the volume of these two are not the same. Therefore, we will need to find out what left in the solution at the end of the reaction by set up the RICF table. Again, for the RICF table unit, we will need to use mole. Therefore, you will need to convert all of these volume and concentration into mole first before you can plug into the initial mole. After you calculate the number of mole for hydrochloric acid and sodium hydroxide, you will see that the mole of hydrochloric acid is less than mole of sodium hydroxide. Therefore, hydrochloric acid would be the limiting reactant. This number of mole will all be consumed. And the same number of mole will be consumed as well for sodium hydroxide in order to neutralize hydrochloric acid. And the same number of mole will be produced for sodium chloride. And at the end, what left would be 0 mole of hydrochloric acid. We will have 0.0001 mole of sodium hydroxide left and 0.0002 mole of sodium chloride left at the end. And at the end of the reaction, you will see that we have strong base, sodium hydroxide left, and we have pH neutral salt left. And because strong base is much stronger than the salt, therefore we can ignore the presence of sodium chloride because it has pH neutral. The only thing that will determine the pH of the solution would come from the sodium hydroxide left in the solution. Because sodium hydroxide is a base contain OH ions, therefore, when we take a negative log of concentration of a base, you are first going to obtain POH, not the pH. Therefore, you will need to convert POH to pH to obtain the pH of the solution at the end. For the strong base, such as sodium hydroxide, the concentration of sodium hydroxide will be the same as the concentration of hydroxide ions because sodium hydroxide dissociates 100% to give hydroxide ions. Therefore, if we know the concentration of sodium hydroxide, we then will know the concentration of hydroxide ions. So first step, we will need to calculate the molarity of sodium hydroxide first by using the mole that is left after the end of the reaction, which is 0.00010 mole of sodium hydroxide divided by the total volume of the solution, which is going to be 20 milliliter add to 30 milliliter, and then convert that milliliter into liter. You are going to get 0.050 liter, and you will get the concentration of sodium hydroxide equal to 0.0020 molar. And again, this concentration belongs to sodium hydroxide, which is going to be the same concentration as hydroxide ion. So if you take negative log of this value, you are going to get POH, not the pH, which come out equal to 2.70. The problem doesn't give us a specific temperature. Therefore, we're going to assume that this happened at 25 degrees Celsius so that we can use the relationship between pH and POH, that pH would equal to 14.00 minus POH. Therefore, the pH of this solution would come out equal to 11.30. And again, this solution at the end of the reaction contain only sodium hydroxide and the pH neutral salt. Therefore, this solution would be a basic solution because you have sodium hydroxide left and your pH should be greater than 7. Next, we are going to take a look at how to calculate pH for the titration solution of the weak acid that is titrated with the strong base. And we are going to sketch this pH curve by looking at what is being titrated. We see that the acetic acid is titrate, so acetic acid is the analyte. with the strong base, sodium hydroxide. So in this case, sodium hydroxide will again be the titrant. Therefore, the graph that we will plot would be plot between the pH of the analyte or the pH of the solution in the Erlenmeyer flask, plot against the volume of the titrant, which is sodium hydroxide. And again, in this case, because the analyte is in the flask, so at the beginning, before the reaction happened, the pH that we are going to measure would be the pH of an acid. Therefore, it would be lower than 7. And as sodium hydroxide is keep adding, the pH will rise until it reaches the end point. It will increase sharply, and then until it passes the end point, it's going to have only sodium hydroxide left, so the pH will continue rising up. And the middle of the steep peak right here, this is the equivalent point where the mole acid equal to mole of base, and the volume of this we call the end point that we see earlier. And again, the pH at this point would be the pH of the end point. For the pH calculation in example 6, we are going to consider point A, B, C, and D. Point A is when we have not add any base yet. Point B when we add small amount of base. Point C would be when the amount of acid base are equal. And point D would be beyond the equivalent point when we have excess base. For point A, before we add any base, the acid-base neutralization reaction have not occurred yet. Therefore, it's only acid left. This acid here is a weak acid, and the weak acid doesn't dissociate completely. Therefore, the concentration of weak acid would not equal to the concentration of the proton that available in the solution. The concentration of weak acid will always be greater than the concentration of the proton that is available, because weak acid dissociate less than 100%. Therefore, the concentration of this would be greater than the proton. That means in this case, in order to find out the concentration of the proton, you will need to set up the Rice table, because when weak acid dissolve in water, it will dissociate and reach the equilibrium. Therefore, we are going to use Rice table in this case. For Rice table, the unit for Rice table would be in molarity or mole per liter. And the reaction would be the reaction between weak acid, acetic acid, and water in an equilibrium to produce acetate ion and hydronium ion. For the initial concentration, it's already given us, which is 0.010 molar. So we are going to fill in 0.010 molar. We can ignore water, and it would be 0 molar for the product. For change, it would be, we don't know how much is changed or how much is dissociated. So we are going to use X for the reactant and product. So therefore, the equilibrium would be 0.010 minus X for the reactant, and X molar for the product. Next, solve for the concentration of hydronium ions at equilibrium, because this concentration will allow us to calculate for pH. In order to do this, you will need to set up the Ka. The Ka expression for this is coming from the concentration of the product divided by the concentration of the reactant. In this case, it would be X times X and divide by 0.010 minus X. And if you want to avoid the quadratic equation, you can ignore this negative X in the denominator. We can neglect this. And plug in the value of Ka. Multiply these two numbers by each other to get rid of the 0.01 right here. And you are going to get the x squared equal to 1.76 times 10 to negative 7. And square root x square to get an x, and you will get an x equal to 4.20 times 10 to negative 4. This x is the concentration of hydronium ion at equilibrium. Therefore, if you take negative log of this value, you are going to get pH of the solution, which equal to 3.38. This solution is a weak acid solution, therefore the pH would be lower than 7. If you compare this pH to the previous example on page 52, you will see that the point A, this pH would be higher than point A of the previous example because this acid is a weak acid. It doesn't dissociate completely, therefore the pH of a weak acid would be higher than the pH of the strong acid. Next, let's take a look at pH at point B. Point B, we have the amount of acetic acid given, and we have amount of sodium hydroxide given, and as you see, the concentration are the same, but the volume are not the same. Therefore, we will need to set up RICF table to look at the neutralization reaction and to find out how many mole left at the end in order to see how can we calculate for the pH of the solution. The neutralization reaction of these acid and base will be acetic acid will react with sodium hydroxide to convert to sodium acetate and water. And because acid-base react in a stoichiometric ratio, therefore you will need to convert the volume and molarity into number of mole first for both of them. After you finish calculating the milliliter and molarity into number of mole, you will see that the number of mole of sodium hydroxide is less than number of mole of acetic acid. Therefore, in this case, sodium hydroxide would be the limiting reactant. The sodium hydroxide mole will be all consumed. So it's going to decrease all of it. It's going to consume all of it. And it's going to use the same amount of mole for acetic acid to react with 0.001 mole of sodium hydroxide. And the amount of salt that will be produced would be the same amount of mole because the reaction is 1 to 1 to 1 mole ratio. And at the end, what left at the end would be 0.0001 mole of acetic acid. There will be no more sodium hydroxide left in the solution, and you will have salt, which is 0.00010 mole left in the solution. And again, to recall how to find out the number of mole at the initial state, you will need to convert molarity into liter and multiply by the concentration, mole per liter. You are going to end up with the mole. If you look at what left in the solution, you will see that the solution has weak acid left. And this solution also has its conjugate base in form of salt as well. As we see that this conjugate base contains CH3CO2 that have one less proton than acetic acid. So in this solution, we have weak acid and its conjugate base. This solution considered to be a buffer solution. And to find out the pH of a buffer solution, we can use Henderson-Hasselbalch equation, which is pH equal to pKa plus log of the concentration of the conjugate base divided by the concentration of the conjugate acid. And as mentioned earlier, because this solution is in the same volume at the end, they both are going to be in the same volume. Therefore, we don't need to convert it into a concentration. We can just use number of mole and plug into this Henderson-Hasselbalch equation. You will get the pH of 4.75. If you compare the pH between point A and point B, you can see that as we add sodium hydroxide into the solution, the pH need to going up because the solution become less acidic and more basic. Now let's take a look at the titration curve. If you look at the point where the volume of the sodium hydroxide is half of the end point, and you trace this back to the graph, and you also trace this back into the pH. Oops, that's a bad drawing. At this point, the pH of the solution will equal to the pKa of a weak acid. Therefore, if you know the pH, you will know the pKa. If you know pKa, you will also know the pH as well. And plus or minus 1 between this region right here, pKa plus or minus 1, we call this region a buffer region. So this is a buffer region or buffer range that we learned earlier. And as you see, the reason why this is a buffer range, because at this point around point B, you can see that what left in the solution would be weak acid and its conjugate base, which is the identity of a buffer solution. And you can use the Henderson-Hasselbalch equation in order to calculate for pH of the buffer solution. Point C is still a base and acid titration reaction. Therefore, we are going to set up the RICF table for this neutralization reaction, and you will need to find out the number of mole that present for each of these two species. After you calculate the number of mole of acetic acid and sodium hydroxide, you will see that the number of mole of these two species are equal. Therefore, both of them would be the limiting reactant. They both will be consumed. Therefore, the change of these two would be negative 0.00020 for both of them. And the amount of the product that will be produced would be the same number of mole. Therefore, at the end of the reaction, you will have 0 mole of the weak acid left, 0 mole of the strong base left. You will have only salt left in the solution. Therefore, at this point, after the reaction has stopped, the amount of the salt that is available will be the one that determines the pH of the solution. This salt that we see is the salt that contains sodium ions and acetate ion. Sodium ion is a pH neutral ion. Therefore, we don't need to worry about sodium ions, but the acetate ions would be a basic ion. Therefore, this basic ion would be the one that determines the pH of the solution. To calculate for the pH of the solution, you will need to set up the RICE table and write the ionization of acetate ion in water. And know that the unit that you need to put in the RICE is mole per liter or molarity, not mole. You might wonder, how do I choose between RICF and RICE table? The RICF table is used when the reaction is involved with the actual acid and base, not with water. These acid-base reactions have to be again with the acid and base, not with water. But the RICE would be the reaction between either acid or base that react with water. Therefore, in this case, because the acid or base that react with water will eventually reach the equilibrium point, we are going to use the equilibrium Rice table. But when you have acid-base neutralization reaction, the acid and base, one of them, if they are limiting reactant, they will be all consumed. Therefore, we will need to find out what is the mole available at the final stage. Therefore, we are going to use RICF instead, because we will need to know the final mole at the end of the reaction. The difference in unit between RICF and RICE is that RICF, you are going to use mole, and the Rice table, you are going to use molarity, which is mole over volume. Therefore, in this case, the number that we are going to plug in here have to be the value of the concentration. We cannot use the number of mole that left in the previous step and use them here, because this number is going to be just the number of mole, is not mole per liter. Therefore, we will need to convert this mole into molarity first. Molarity of the sodium acetate after the end of the reaction will equal to mole divided by the liter. In this case, the mole that we have is 0.00020 mole. And the volume that this salt is present in would be the addition between these two, right? It's going to be the total volume. So it would be 20 plus 20 milliliter. Convert that into liter. You are going to get 0.040 liter. And the concentration of sodium acetate will come out to be 0.0050 mole per liter. And the salt, sodium acetate, is a strong electrolyte, which means that it's going to dissociate completely, which means that the concentration of the strong electrolyte sodium acetate would then equal to the concentration of the acetate ion. Next, plug in the concentration of the acetate ion into the rice table. Ignore water, and it would be 0 for the product, and change would be negative x because we don't know how much it changed, and positive x for the product. And equilibrium would be 0.0050 minus x and plus x for the product. The product. Next, write out the equilibrium constant expression K. K in this case would equal to the concentration of acetic acid multiplied by the hydroxide ion and divide by the acetate ion concentration. And you can see that because this reaction produces hydroxide ion, therefore the equilibrium constant expression that we write here would represent Kb, which is the equilibrium constant of the base because produce hydroxide ion. However, the problem gives us the Ka value of its conjugate acid. Therefore, you will need to convert this Ka into Kb first in order to plug into this value right here. And the Kb would equal to Kw divided by Ka. And Kw at 25 degrees Celsius is equal to 1.0 times 10 to negative 14 divided by the Ka value that is given, which is 1.76 times 10 to negative 5. You are going to get the Kb value of 5.68 times 10 to negative 10. And then choose the concentration at equilibrium for all the species. And plug into the Kb expression. And again, to avoid the quadratic equation, we can ignore the negative x at the denominator. And so for x, you will get the value of x equal to 1.685 times 10 to negative 6. And this x is actually equal to the concentration of hydroxide ion at equilibrium. Therefore, in this case, concentration of hydroxide ion would equal to 1.685 times 10 to negative 6 molar. If you take a negative log of this value, you are going to get POH. And the POH will equal to 5.773. The last step is to convert POH into pH. We will need to subtract this number from the 14 and you will get the pH of 8.23. Let's check our answer. This salt is a basic salt and your pH should come out higher than 7 and our calculated pH is higher than 7, so this answer is valid. Now let's take a look at point D. Again, point D is the reaction between weak acid and a strong base. So the type table that I'm going to set up is RICF because it's not the reaction with water. So I'm going to set up RICF the same way that we did earlier, and then we are going to plug in the number of mole of each of these species into the initial mole. And you will see that the initial mole of weak acid, acetic acid, is less than sodium hydroxide. Therefore, in this case, the acetic acid would be the limiting reactant, and the number of mole that will be consumed would be 0.0002 mole. And same as for sodium hydroxide as well, because you need to use the same mole to neutralize acetic acid. And the same number of mole will be produced for the salt. And the final mole would be the difference between the initial and the change. So we have 0 mole for the weak acid left. We have 0.0001 mole of strong base left. And we have 0.00020 of the salt left. At this point of the solution, you will see that we have the strong base sodium hydroxide left in the solution. And we have a salt that is a basic salt that left in the solution. How do we determine the pH of this solution then? The pH of this solution will be determined from the strong base. Because strong base is a lot stronger than the salt, therefore in this case the strong base will override the pH of the basic salt, so the strong base will determine the overall pH of the solution. So in this case we can ignore the pH of the salt. We have to only consider the pH from sodium hydroxide. And because sodium hydroxide contains the OH ion or hydroxide ions, therefore if you take negative log of the concentration, you are going to get POH. Then you are going to convert that into pH at the end. And we know that POH is need to be a negative log of the concentration. Therefore, we will need to first find out the concentration of sodium hydroxide present in the solution. Because concentration of the strong base sodium hydroxide will equal to the concentration of hydroxide ions. In order to find out the molarity of sodium hydroxide, we are going to divide the available mole of sodium hydroxide that left in the solution by the total liter of the solution, which would come from the 20 add to 30, so total would be 50 milliliter. Convert that into liter, you are going to get 0.050 liter. And the concentration of sodium hydroxide will come out to be 0.0020 molar, which is the same as the concentration of hydroxide ion. Therefore, if you take negative log of this value, negative log of 0.002 molar, you are going to get 2.70, which is going to be the value of POH. And again, the problem doesn't specify the temperature. Therefore, in this case, we are going to assume that it's at 25 degrees Celsius. Therefore, the relationship between pH and POH would be pH would equal to 14 minus POH, which is going to be 14 minus 2.70, which is equal to 11.30. And this solution is contain the strong base sodium hydroxide. Therefore, the pH of the solution would be a lot higher than 7. In summary, for the titration of the strong acid and the strong base, here are the points for each of the steps throughout the titration curve. For point A, to find out the pH of point A, you will need to first find out the concentration of the strong acid. Because strong acid completely dissociates, so it's going to be the same as the concentration of proton. Therefore, if you take a negative log of the concentration of the strong acid, you are going to get the pH of the solution at point A. For point B, when the acid and base react in point B, you are going to set up the RICF table and using mole to find out what are the leftover mole. At this point, the leftover mole would be the mole of the strong acid. The strong acid that is left over, you will need to convert its mole into the concentration by dividing with the whole volume, the overall volume in liter, and then the concentration of the strong acid will equal to the concentration of the proton. Because strong acid dissociates completely, therefore if you take negative log of the concentration of the strong acid, you are going to get the pH of the solution at point B. For point C, this is at the equivalent point. At this point, there is only salt left in the solution. There is no more acid or base at this point because those two moles are equal. They already neutralize each other. So we have only salt left. And the salt that produced from strong acid and strong base is a neutral salt. Therefore, the pH at this point would equal to 7. And for point D, this is beyond equivalent point. This is when you will need to set up the RICF because it's the neutralization reaction between acid and base. They react with mole to mole ratio. Therefore, you will need to first find out number of mole for acid and base and plug into the RICF table to find out what is the leftover mole at this point. The leftover mole of this point would be the mole of the strong base. Therefore, you will need to obtain the mole of the strong base and then convert to the concentration of the strong base by dividing by the overall volume in liter. And because strong base is going to give off hydroxide ions 100%. Therefore, the concentration of the strong base will equal to the concentration of the hydroxide ion. So if you take negative log of this strong base concentration, you are going to get the pOH. And then to find out the pH at 25 degrees Celsius, you will subtract from the 14. Next, let's take a look at the summary of the titration between weak acid and the strong base. The pH curve will be similar to of the strong acid and strong base here. We are going to look at each of these points specifically. For point A, this point A for the weak acid is have only the weak acid left. Because concentration of weak acid is not equal to the concentration of the proton available in the solution, therefore you will need to set up rice table by doing the ionization of the weak acid in water, react weak acid with water, set up rice table, use Ka to solve for the concentration of proton or hydronium ion at equilibrium, then take negative log in order to get the pH of the solution at point A. For point B, you will need to set up RICF table because point B is when the acid and base react together. So you will need to set up the neutralization reaction between acid and base and find out number of mole for each of those species at point B, and then plug into the initial and change mole, and then find out what is the final mole. You will see that at the end, the final mole that is left would be the final mole of the weak acid and its conjugate base in form of salt. So this solution is considered to be a buffer solution. Therefore, to find out the pH at this point, you can use the Henderson-Hasselbalch equation. And at this point, if you trace the volume at the equivalent point, which is point C, this volume is the volume of the endpoint. Half of this volume, which is 1/2 of the volume of the endpoint. For example, if the endpoint is 100 milliliter, half of the volume would be 50 milliliter. If the volume at the endpoint is 50 milliliter, then the volume, half of the volume at the endpoint would be 25 milliliter, for example. And if you trace these to the pH scale, you will see that at this point right here, pH would equal to pKa. So that means if you know the pH at the half of equivalent point, you can say that is equal to pKa. And again, pKa plus or minus 1, this range will tell you the buffer range. So within this range of plus or minus 1, this range right here, we consider this range to be a buffer range. And for point C, again, we are going to react acid and base again because they are going to neutralize by each other. So you are going to set up RICF table, find out mole of the acid and base, plug into RICF table mole to find out number of mole left at the end. And you will see that at the end, at this point C, there will be no more acid and base left. The only species that left in the solution would be the mole of salt. Then you are going to convert this mole of salt into concentration of salt, and then hydrolyze this salt into cation and anion. And you will see that the anion is the one that is going to ionize in water or react with water. And you are going to write out this ionization in water of the anion into the rice table. Then use the concentration to plug into here in the rice table. Use the Kb value to find out the concentration of the hydroxide ion at equilibrium. Then take negative log to get pOH and then convert that into pH. For point D, you are going to react acid and base again. So you will need to set up RICF table to find out how many mole left in the solution. And you will discover that the amount of mole left in the solution would be the mole of strong base. Then you will need to convert mole of the strong base into the molarity of the strong base. Then because strong base is giving off 100% of hydroxide ion, so if you take a negative log of the concentration of the strong base, you are going to get pOH and convert that into pH. This concept is very challenging. You will need to practice more of this concept in order to master in it. Without practicing, you will not be able to do this concept at all. And to practice more, please complete the DIY problem on page 55 and the answer key for this will be posted on Moodle. The last section of this chapter is acid-base indicator. Acid-base indicators are either weak organic acid or weak organic bases. This indicator in water, it will ionize. For example, if you have the indicator that is made of complex weak organic acid molecule, as indicated here, when it's dissolved in water, it will react with water to produce hydronium ion and its conjugate base. The indicator and its conjugate base will have different color. For example, if we have the indicator with the color of green, and if we have the color of its conjugate base red, when the equilibrium got disturbed, we will see the color change between green and red. According to the Le Tellier principle, if the indicator is present in an acidic solution, for example, in this case, the acidic solution will have high concentration of the hydronium ions. Therefore, as the concentration of hydronium ions increase, it's going to make the reaction shift to the left toward the green color. Therefore, the indicator will appear in green. However, if this indicator is present in less acidic solution or more basic solution, that solution will have low concentration of the hydronium ion. Therefore, the reaction will shift to the right to produce red color. Therefore, the indicator will change to red color. Here are an example of the acid-base indicator. You can see the color change interval, and this is between the pKa plus or minus 1 of each of these weak acid and weak base indicator. Now let's take a look at example 7. The pH at the end point of the titration between a certain weak acid and a certain strong base is 8.5. Choose an appropriate indicator for this titration. Explain how the color would change. So if you want the titration that have the end point which is at 8.5, which means that you will need to find the color that is fall into this range, because this range will tell you that the color will need to change around this range. If it's outside this range, you will not observe the color change at all, so you will not know when to end the titration or when to stop the titration. If you look at the acid-base indicator that's given here and find out the pH range at around 8.5, this range fall into this indicator, this indicator, and 3 more. So which one should we choose then? I would not choose chrysolite. The reason for that is because under acidic condition it's going to become yellow, and it's going to change color around 7.5, and anything above 8 is already red. Therefore, you will not see the color change at 8.5. So if you choose this indicator, you are going to stop titration before it's reached the end point. Now the second option for the indicator is thymo blue. Thymo blue, when it's acidic solution, is going to appear in yellow. When it's basic, it's going to appear in blue. And you will see that this color change will happen around 8.5. Therefore, when you have an acidic solution, it's going to be yellow up until it reaches 8.5. Then the reaction will change to green. And beyond the equivalent point, then the reaction will change to blue. So this would be a good choice for indicator for this titration. Now, if you look at phenol red has the same analysis as chrysolite. At this point, you will see only red. You will not see the color change. The color change happened before that. Therefore, if you choose this indicator, you are going to stop titration before the end point. So that means it's going to give you an inaccurate data. Same thing for the nitrophenol as well. It's already changed to yellow at 8.5. Therefore, this indicator will not be appropriate because it is going to change color before it's reached the end point. Now for the chrysophthalene, this one you will see that the color is going to change between colorless to pink, and you see that the changing area is around 8.5. Therefore, this would be a good indicator to use as well, because you are going to see the color change from clear to pink or red in this case at 8.5. Another one is phenolphthalein. Phenolphthalein is changed the color around 9. So therefore, in this case, you might not be able to capture that change. You might already overshoot it, which means that you are adding more of the base than the acid before you can see the color change here. So that means the best choice of this indicator would be the thymo blue, and it would be the chrysophthalene.